Hi YouTube, my name is Michael Behringer. I'm a medical doctor and a full professor of sports medicine and exercise physiology at Goethe University, Frankfurt, Germany. Today's video will be all about tensiomyography, or abbreviated TMG. This is a non-invasive technique to assess muscle contractile properties, and we will take a look at what the method measures, what it can tell us about muscle function, and we will start with a short demonstration on my forearm muscles, so let's do this. So first of all, tensiomyography, or TMG, is a method used to assess the mechanical reactions of a muscle to a brief electrical stimulus. So it provides an objective and non-invasive insight into how muscles behave, particularly their contractility. So that muscles maintains a near constant volume, so when it contracts along its length, it will expand radially, and TMG captures exactly this radial expansion over time using a highly sensitive sensor placed on the muscle belly, and you can see this sensor here. So this is the sensor that will be placed on the muscle belly. The resulting curve that we can see then in the software tells us how the muscle deforms over time, so how fast it contracts and how quickly it returns to the resting situation. These features provide insights into the neuromuscular function and training effects, fatigue, or even damage. This is why we use it, for example, in research. So, although TMG is influenced by factors like stiffness or tone, it primarily reflects an active contractile behavior. So it's not just a stiffness measurement. Those things are often mixed up. So let's do this live demonstration. You can see, as I said, the sensor here, and we will place that on my forearm muscles. Why the forearm? It's just because they're easily accessible here. So I will try to do that on my own. Usually another person is doing that, of course. So you can place the sensor, and you don't need much to do that. You will place the sensor, for example, here on the forearm muscles. You can use two electrodes placed very closely together in the near proximity of the sensor. And then you can hit a button in the software and it will start the measurement. Doing so will not change anything here because the electrical stimulator is still set to 0 milliamperes. So we have to increase the amplitude a little bit. So we'll start, for example, for that demonstration purposes, at 20 milliampere. So new measurement, we will measure, and then you will see as soon as I hit the button that the muscle will contract. This is now very low amplitude, so we don't expect a huge expansion here. So that was, I don't know if you have seen that, but that contracted my muscles. I can see now a curve of this displacement on the screen. So, but now we will increase the amplitude, so I will go up for demonstration purposes in larger steps now. So I go up to 50, around 50, and hit measure again. And as you've seen, not only my muscles moved, but of course also the wrist, which is moved by the forearm muscles. And we will increase now again up to 70, for example. And I will hit measure again. So usually you do that repeatedly until you reach a maximal visible displacement. So you will check the curve and the software, and if increasing the amplitude does not change the curve anymore, then you know that this is the maximal displacement. So what does this curve now actually tell us? First of all, I will get rid of the sensor in my forearm. So now I can move that out of the way. Okay, so this curve now gives us an idea about the contraction over time, and the software automatically provides you with some parameters. One of the parameters, and maybe the most important one, is DM. This is the maximal displacement, and it reflects the muscle contractility, and it is influenced by stiffness and tone, and it is influenced by fatigue. Then you can see TD. TD is the delay time. So the time from the stimulus, the electrical stimulus, to 10% of DM. And this reflects the excitation-contraction coupling. Then you can see TC, and TC stands for contraction time. So from 10% to 90% of DM, and this is related, interestingly, to the fiber type. We will come to that in a minute. Then you have TR. R is for relaxation, so TR is the relaxation time, and this is the time to return from peak DM to 50% of DM. And then there is something which is not automatically provided by the software, but is frequently used in the literature, is VC. So this is the contraction velocity, and this is calculated from DM and TC, indicating a dynamic performance of the muscle. So contraction velocity, as I told you, is usually used in the research literature because TC is largely affected by the muscle mass, for example. So velocity is here a little bit more fair, if you want. And one of my PhD students has shown that different VC calculations are out there. So how to calculate VC from the delay, the displacement, DM, and the contraction time. And the result is VC is highly reliable, especially in the rectus femoris, and it's consistent across stimulation protocols. So this supports that VC is a robust and valid index for tracking dynamic muscle performance. What does science now say? So what can we actually do with this method? What does it tell us? First of all, and I think it's very interesting, that TC, so the contraction time, correlates well with the fiber type. So usually if you want to know something about the fiber types within your muscles, you know, there are fast twitching fibers and there are slow twitching fibers, and usually you need muscle biopsies from your muscles to know, do you have more of the slow contracting fibers or more of the fast contracting fibers? But it has been shown in the literature that TC correlates with the amount of type 1 fibers by 0.85. So that's quite a good result here. Furthermore, there are other results out there, for example, by Lohr and colleagues. They confirm that TMG is sensitive to fatigue. So post-fatigue, the TC is increased and the DM is usually decreased. And these changes reflect slower contraction speed and a reduced compliance of muscles, which is very interesting. So you can use TMG to assess muscle fatigue. Furthermore, we can use this tool for the measurements after an injury. So for example, after an injury, muscle contractile properties change, and TMG can detect and track these changes. And this is especially valuable in early rehabilitation phases where the objective diagnostics are very limited. And TMG has differentiated injured versus healthy hamstrings with over 80% accuracy, and I think this is very interesting too. So if you have a player on the one side, a soccer player for example, on the one side the hamstring muscles are injured and on the other side not, you can compare both sides and track the rehabilitation process, for example. Of course, there are limitations. So TMG results are sensitive to the sensor placement and fixation. And the TMG doesn't measure voluntary activation or coordination. So of course, it makes sense to combine this measurement with other measurements like force measurements or EMG or other performance tests. So this is, in my eyes, a very interesting technique to complement others, and of course, it's not a panacea to replace all other measurements. So in summary, TMG is a reliable and a non-invasive measurement. It offers insights into contractility, the contraction speed, and fiber composition, and best used with standardized protocols. This is important, and it is ideal for tracking training, fatigue, injury recovery, and muscle atrophy. And I think, therefore, the TMG is a very interesting tool, not only for research purposes where we use it, but also for the field, for example, for the use for physiotherapists, for example. So I hope that gave you an interesting overview about the TMG procedure. And yeah, I hope you like this video. Check out our next videos and see you soon. Bye-bye.